Welcome to a lesson on solving a first-order homogeneous differential equation written in standard form. A first-order differential equation in the form dy dx equals f of x comma y is homogeneous if it does not depend on x and y separately, but on the ratio of x to y or y to x. So we can say a differential equation is homogeneous if it can be written in the form of dy dx equals f of y divided by x or x divided by y. So we'll first check to see if the given differential equation is homogeneous, and then if it is, we can solve it by performing substitution. We'll perform the substitution v equals y divided by x, but since we'll also have to perform a substitution for dy dx, if we solve this equation for y by multiplying both sides by x, we can say that y is equal to x times v, and then to find dy dx, we'll have to perform implicit differentiation and the product rule. So dy dx is going to be equal to x times dv dx plus v times the derivative of x, which would just be 1. So for the substitution, we'll use v equals y divided by x and dy dx equals x times dv dx plus v. Once we perform this substitution, we can solve the resulting differential equation using separation of variables, and then we'll solve the original differential equation in terms of x and y. So let's take a look at our first example. So our first step is to see if this is homogeneous by seeing if we can write the right side of this differential equation as a function of y divided by x, shown by our notes here below. Now here, because we're dividing by a monomial or one term, we could break this up into two individual fractions. But another way to approach this would be to recognize that if we have a y squared here, we want this to be a ratio of y to x. Our denominator of this term would have to be x squared. So we can multiply the numerator by 1 over x squared as long as we do the same to the denominator. Now if we look at the denominator, notice how we'd have x squared over x squared. So this product simplifies to 1. And now looking at the numerator, if we distribute here, we'd have 3 times y squared over x squared, which we can write as 3 times y divided by x squared, plus, here we'd have xy over x squared. Notice that one factor of x would simplify out, leaving us with just y divided by x. Notice how the right side of this differential equation is a function of y divided by x. Therefore, we know this is a homogeneous differential equation, so now we'll perform a substitution and solve this using separation of variables. And again, the two substitutions we're going to use are v equals y divided by x, and if we solve this for y, we'd have y equals x times v, and then applying implicit differentiation, we would have dy dx equals x times dv dx plus v. So we'll use these two equations to perform a substitution into our original differential equation. So instead of dy dx, we're going to have x times dv dx plus v. So here's dy dx equals, now 3 times y divided by x squared is now just going to be 3v squared. And then y divided by x is just going to be v. And now we can solve this using separation of variables. Notice that we have a plus v on both sides of the equation. So if we subtract v on both sides, these two terms would simplify out. So we'd have x times dv dx equals 3v squared. Now we want the x's and dx on one side and the v's and dv on the other. Now because the dx is in the denominator, we want the x terms on the right side. So we're going to go ahead and multiply both sides by 1 over x. We want the v terms on the left side, so let's also multiply by 1 over 3v squared. When we do this, notice how these x's would simplify out, and on the right side, the 3v squared would simplify out. So let's go ahead and write the left side as 1/3 v to the negative 2 dv dx equals, on the right side we just have 1 over x. And now we'll go ahead and write this in differential form, which we can think of as multiplying both sides by dx. So we'd have 1/3 v to the negative 2 dv equals 1 over x dx. And now we'll integrate both sides of the equation. So applying the power rule here, we'd have 1/3 times v to the negative 1 divided by negative 1, or negative 1/3 v to the negative 1. Now there would be a constant of integration here, but we'll go ahead and put it on the right side. So this is going to be equal to the integral of 1 over x would be natural log absolute value of x plus c. Let's go ahead and continue this on the next slide. Let's go ahead and write this back in terms of x and y. So if v equals y divided by x, v to the negative 1 power would be x divided by y. So we'll have negative 1/3 times x divided by y equals natural log absolute value of x plus c. Let's go ahead and eliminate this fraction by multiplying both sides by negative 3. So we'd have x divided by y equals negative 3 times natural log absolute value of x. Then we'd have minus 3c, but let's let c sub 1 equal negative 3 times c. That way we can just write plus c sub 1. This would be the solution to the homogeneous differential equation, but let's go ahead and solve this for y. We could think of this as all over 1, then take the reciprocal of both sides, so we'd have y over x equals 1 over, let's write c sub 1 minus 3 natural log absolute value x. Now the last step here, we can multiply both sides by x, so we'd have y equals x divided by the quantity c sub 1 minus 3 natural log absolute value x. And this would be our general solution to the original homogeneous differential equation. Let's finish by taking a look at this graphically. The red slope field that we see here can be generated by using the original differential equation, and then here's our general solution. And what I did here was graphed several of the possible solutions with c equals negative 2, negative 1, 0, 1, and 2. So each graph below that's a different color represents one of the solutions from the family of solutions. In part 2, we'll take a look at a second example of solving a first-order homogeneous differential equation. I hope you found this helpful.